All right. So welcome back, everyone. Hope you had a good recharge day, at least as much as you could, being in the middle of the week. Let's go ahead and start lesson 26. So last time in lesson 25, we learned how to find power series representations of different functions. So we learned how to find them for rational functions, and then we also saw some ways that we can get them for logarithms and arctangents as well. So what we're going to be doing today is we're going to put this knowledge to use, and we're going to do some problems that would have been difficult or impossible earlier without the help of power series. So for our first example, what are we going to do for this? We're going to do the integral from 0 to 1 of arctan of x squared dx. And so what I want to do is I want to approximate this integral with an error less than 0.01. I don't want to be any more than 0.01 off from the true value of this integral right here. Now you might be like, okay, well, why don't we just do that integral normally and then plug in 1 and 0 and then get like the actual answer to this rather than just approximating? Well, I don't know about you, but I don't really think I'd want to do the integral of arctan of x squared. So the way we would do this if we want to do it for real is we would do integration by parts with u as arctan of x squared and dv being dx. But even if you did that, and that's probably the only way I know of doing this integral, you would have a really terrible rational function to integrate afterwards. So while this is technically possible to do, it's not very pleasant at all. So rather than get the exact answer with a lot of grief, we can do something a lot easier and get an approximate answer to a pretty high degree of accuracy here. So what we're going to do is instead of integrating this kind of nasty function, arctan of x squared, we're instead going to integrate its power series. And integrating a power series is always easy because a power series is essentially a giant polynomial. And we just keep doing the power rule on. So first of all, we need to come up with a power series for arctan of x squared. Why don't we start with arctan of x? I think we saw a series for this last time. I think we did this as practice. The series for arctangent of x is the sum from 0 to infinity of -1 to the n, x to the 2n plus 1 over 2n plus 1. I think we got something like that for a practice problem last time. So we know what the series for arctan of x is. And even if we didn't, we could have found the series for 1 over 1 plus x squared and integrated it to get arctan. So we could have gone back further if we needed to. But if we don't want just arctan of x, right? We want arctan of x squared. So what do you think, how do you think we're going to get arctan of x squared? What do I need to change about the series in order to make it be arctan of x squared? What's going to be different? Yeah, you just square the term with x in it, right? So this will be -1 to the n x squared to the 2n plus 1. Well, by exponent rules, I multiply those, and I get -1 to the x to the 4n plus 2. So this is going to be my series for arctan of x squared right here. All right, so now that I know what this is, I can integrate this series instead of this function. Now, one thing we want to be cautious of, remember, we can't just use any x values we want in any old series. All of the x values need to be in the interval of convergence. And the same thing goes with integrals. If we integrate it outside of the interval of convergence, this series may not represent the function anymore. Does anyone remember the interval of convergence for arctan? What was that? You guys remember what we got for that? Yeah, -1 to 1. Did we include the endpoints or exclude them, or maybe include one and exclude the other? We included both of them, that's right. Okay, and that's good news here because the interval from 0 to 1 is entirely contained right here. So that means that we're going to be within the interval of convergence the whole time, meaning that we can use this series in place of this function. All right. So let's see here. So if we're doing the integral from 0 to 1 of arctan of x squared dx, that's the same thing as doing the integral from 0 to 1 on the series n equals 0 to infinity, negative 1 to the n, x to the 4n plus 2 over 2n plus 1. Okay, now remember, how do we integrate power series? And the answer is very easily. What we do is we move the integral right next to wherever the x is. So any of the stuff with n's doesn't contribute anything. All we're doing is we're doing the integral of x to the 4n plus 2 right here. And what's the integral of x to the 4n plus 2? Well, we just use the power rule. So we raise this power by 1. So now it's x to the 4n plus 3. And then we divide by our new power. So in addition to having a 2n plus 1 down there, we will also have 4n plus 3. And now just like any other integral, any other definite integral, we evaluate this from 0 to 1. All right, let's see what happens if we plug 1 into here. Well, we have 1 to the 4n plus 3. Well, 1 to the anything will be 1. So we're just going to have negative 1 to the n over this stuff here. And then we're going to plug in 0, but 0 times any of these coefficients, no matter what our n is, will be 0. So we don't need to have that. So it turns out that our integral is exactly equal to our series right here. So we can use an exact equal sign if we include our entire series. Now, in reality, even a computer is going to have great difficulty adding together infinitely many terms manually. So what we're going to do is we're going to add together the first few terms and hope that our error is less than 0.01. What happened to the x? We plug 1 in for the x right here. So we have 1 to the 4n plus 3, but that's just going to be 1. All right. So now one nice thing about this series, what type of series is this? It's an alternating series. That's right. So the nice thing about alternating series is that we had that one result about them that let us know the error in using the partial sum instead of the full sum. So since this is an alternating series, we can use the error estimate for that. All right, now let's review how that works. What we're going to do is we're going to look at the stuff that's multiplied by the negative 1 to the n right here. And we're going to keep plugging in higher and higher n until this is less than what we want our error to be. So remember, our error, we want that to be less than 0.01. So we want our error less than 0.01, which is 1 over 100. So I'm going to start plugging in n values. This is going to be an. And I'm going to keep plugging them in until I'm less than this. So let's start at 0. Maybe we're really lucky and 0 will just do the trick. So we have 1 over, well, I guess it'll be 1 times 3. So it's 1/3. Okay, 1/3 is not less than 1 over 100. So we can't do that. All right, how about n equals 1? Well, let's see. I plug 1 into here. I have 3 here, and I have 7 here. So I have 1 over 21 from that. Okay, a little bit better, but still not less than 1 over 100. Let's plug in n equals 2. If I plug 2 in here, I have 5. If I plug 2 in here, I have 11. So this is 1 over 55. All right, we're getting closer, but we're still not less than 1 over 100 yet. Maybe 3 will be enough. So I go to 3. I plug 3 into here. I have 7 for this, and then I have 15 for this. And 7 times 15 is 105. All right, so we finally found a term that is less than our error tolerance of 1 over 100 right here. So what does that mean? Well, remember that the error estimate says that the difference between Sn and the true sum of our series is less than an plus 1. So that means that if this is 3, 3 was the first one to be less than 1 over 100, then our S is going to be 2. The n we're going to use here is 2. So S2 is what we're going to use. So we use whichever one we had before we got to the one that went under the threshold here. So we're going to stop at 2. So this will be A0 minus A1 plus A2 if we include the alternator. And we already figured out what these were. This is 1/3 minus 1 over 21 plus 1 over 55. And this is our approximation for the true sum of this series right here, which is this integral. So there we go. So we managed to approximate this integral as the sum of these 3 fractions, and we know that the error for this is less than 0.01. All right, well, let's test this to make sure. So S2, if you combine all these fractions and look at the decimal for this side is going to be 0. Let's see, I did this on my calculator earlier. 303,896, like that. And then apparently, according to Wolfram Alpha, who can do the exact version of this without too much effort, this is 0.29790. So we have the difference effectively between 0.303 and 0.297. That's about a 0.006 difference in value. So we see we did end up having a less than 0.01 error here. And we only needed 3 terms to do it. It always feels like, oh, I'm only adding together the first 3 of infinitely many terms. That sounds like it's not going to do very much at all. But really, you can end up getting really accurate approximations with just a very small number of terms. It's typically something like 3 for most error calculations. All right. So why don't you guys give this a try? And I'm going to give you more time than usual because, as you can see, this is a bit lengthy here. But don't worry, we'll end up going over it. What I want you guys to do is I want you guys to do something similar. I want you to approximate the integral from 0 to 0.5 of ln of 1 plus x cubed. And I want the error this time to be less than 0.001 or 1 in 1,000. And at first you might be like, oh boy, now I'm going to have to go out to 10 terms. Trust me, it won't be that many terms. And as a hint here, let me get you started. ln of 1 plus x is the sum from n equals 0 to infinity of negative 1 to the n, x to the n plus 1 over n plus 1. And the IOC is negative 1 to 1, like that. Can I explain the S2 part? Yeah, so we saw, well, I'm not going to cover that up. So we saw that the first AN to be less than our error tolerance was the third one, right? So that's going to be the thing associated with our error. So that means that this needs to be A3, but that's 1 bigger than the number I should have here. So that means I'm going to use S2. So I use whatever number came before the one that finally passes the threshold here. What was on the bottom of the fraction? Oh, this is, sorry, it's an n plus 1 right here. How do you get these representations? Oh, that's what we went over last class here. So what I'm going to do in the future is for the exam, both the exam 3 and the final, you guys are going to have a list of common series representations. So for something like this, you would probably be provided this on a problem or something like that. But if you didn't have such a sheet handy, you would integrate 1 over 1 plus x. And we learned in class how to find the representation for this last time. Well, let me leave this so you can see a little bit. That's right, Diego. Well, what you do to the x right here, whatever you do to this x is the same thing as doing it to just this x here. So if you cube this x, that's the same thing as just cubing this right here. The 1 is just part of the formula. So you don't need to worry about cubing the 1 or anything like that. You're only cubing the x, or rather you're substituting x cubed in for the x. All we need to do is make sure that the integral bounds are in the IOC. So 0 to 1/2 is in here, so we could do this. But in the real world, like let's say we wanted to do the integral from 0 to 2, then we would need to find a different series for this because this only goes out to 1. And we'll talk about issues like that in a future class. Don't worry, Thomas, we'll go over it in a minute. Well, maybe a little more than that. These ones take a while. Seems like people think 1/64. All right, let's go ahead and get started on it, but feel free to keep working on it as I'm talking through the earlier parts. All right, so our whole goal is to do this integral, ln of 1 plus x cubed from 0 to 0.5. And again, I think this is one that is technically doable using techniques we've learned in class, but it is certainly not a fun integral to do. You're going to have to do a lot of weird factoring and partial fractions and probably completing the square and trig sub along the way. It's not going to be great. So rather than do that, let's go ahead and just approximate the value to a pretty high degree of accuracy. All right. So we first need a series for ln of 1 plus x cubed. Now, from last class, we saw that ln of 1 plus x is this sum right here. And if we forgot what this series was, we could do the series for 1 over 1 plus x and integrate it to get the one for ln of 1 plus x. All right, so ln of 1 plus x is this right here. So if we want ln of 1 plus x cubed, we simply replace the x in here with an x cubed. All right. And then we apply exponent rules here. We have x to the 3n plus 3. All right, so this is going to be our series for ln of 1 plus x cubed. All right, now that we know what that is, let's go ahead and do our integral. Now, doing the integral of this directly is very difficult, but as always, doing the integral of a power series is easy, no matter what the power series is. Okay, so remember, the way to integrate any power series that we want is to just move the integral next to the x to the power, ignoring everything else. And then we do the power rule here. So this is going to be, oops, there's a little room here. There we go. So this will be the sum from n equals 0 to infinity of -1 to the n, x to the 3n plus 4, and then we have n plus 1 times 3n plus 4. Oh, and this was a definite integral. This goes from 0 to 1/2. All right, so let's go ahead and plug in this into here. So we have -1 to the n, and then this will be 1/2 to the 3n plus 4. But that's the same as having 2 to the 3n plus 4 down here, times n plus 1 times 3n plus 4, like that. All right. And then we plug 0 in for this, and we get, well, 0. Okay, so let's see here. So now, once again, this is an alternating series, right? And this is exactly equal to our integral. This is exactly equal to our integral, but like I said, even the best computers can't sum infinitive terms. Yeah, what's up? Yeah, so what I did was I plugged 1/2 to the 3n plus 4 in here, right? So this is 1/2 to the 3n plus 4. So 1/2 to a power, 1/2 to the n is the same as 1 over 2 to the n. So this 3n plus 1 or 3n plus 4 went to the 2 on the bottom. All right, so let's see here. Okay, so this is an alternating series, so we can use the alternating series error estimate. Okay, so how do we do that? Well, let's make a little table and start going through our a sub n's. And remember, the stuff next to the alternator is a sub n's. We shouldn't have any negatives for this. All right, let's plug in n equals 0. If we plug in n equals 0, let's see, what are we going to have here? We have 1 over 2 to the 4th times 1 times 4. Okay, 2 to the 4th is 16 times 4 is 64. Now remember, what's our goal here? Remember, our error needs to be less than 1 over 1,000. So you might be mentally preparing to buckle up and plug in a lot of numbers here because we're only starting with 1 over 64, but we need to get to 1,000. Now let's start with n equals, let's go next to n equals 1. If I plug n equals 1 in here, what am I going to get? I'm going to have 1 over 2 to the 7th times 1 plus 1 is another 2 times 3 plus 4 is 7. Now let's see here. 2 times 2 to the 7th is 2 to the 8th. 2 to the 8th is 256. Now, let's see here. Is 7 times 256 going to be bigger than 1,000? Is that true? Yeah, about 4 times this would already be bigger than 1,000, but if we have 7, that's definitely going to be bigger. In fact, I think someone put this in the chat. Yeah, I think this ends up being 1792. We do this all out. But yeah, so this is definitely less than 1/1000. All right, so we arrived at our goal right away, actually. We stopped at n equals 1. So what does this mean? Well, if we look at what we did on the previous thing here, oops, there we go. Once we got to our goal, we cut it off 1 before that. So we got to our goal at 3 here, so we only did 0, 1, and 2. Now we got to our goal at 1 here, so we're just only going to have 0 for this. So what we're saying is we're just going to use S0, which is A0, which is 1/64. And this term alone, this single term, is going to be our approximation for this entire integral. And we know from doing the error estimate here that 1/64 is less than 0.001 away from the true result. So not only did we get an approximation with fewer terms than the last time, it's even more accurate than the one we got in the last problem, which seems kind of crazy. How will we get even more accurate approximation with fewer terms? I mean, I guess it's a different function, so it's a little bit of an apples to oranges situation. But one thing that's interesting about this, one difference we have from the last problem, is that we went out to 1/2 here, but in the previous problem, we integrated all the way out to 1, which is on kind of the bleeding edge of the interval of convergence. And what this is saying is that the closer we get to the center of the IOC, the better the series serves as an approximation. So that approximation we did on the first problem was totally fine. We were within the interval of convergence the whole time. But the reason why I took more terms to get, honestly, less accurate than this one is because we go all the way out to kind of the edge of the series' jurisdiction. The series is not going to represent arctangent if we go anywhere past 1 right here. Whereas we kind of have some wiggle room here. We can go a little bit further because our interval convergence went out to 1. So that's why this one ended up being more accurate than the previous one. All right. In addition to doing integrals, we can actually use series to do something simpler, but probably debatably more important. We can use series to get weird values of different functions. So for example, in pre-calc and stuff like that, you guys probably had to learn the values of, like, say, sine and cosine for specific angles, like pi/3, pi/4, pi/6, pi, etc. So you know what those are. But let's say, for example, you want to know what, like, sine of 1 is, like not 1 degree, 1 radian. Like, how are you supposed to figure that out, sine of 1? And how is anyone supposed to figure that out? Well, your answer might be, okay, well, I'll plug it onto a calculator, but then that just pushes the question back one. How does your calculator know what sine of 1 is? Did someone manually input sine of every single value into your calculator? And the answer is no. That would take longer than all of history to do that. The way that your calculator knows what sine of 1 is because it uses the power series for sine of x. And if it wants to do it for a log, it uses the power series for a log function. When you do it for arctangent, use the power series for the arctangent function. So we're going to kind of pretend to be a calculator here, and we're going to use this reasoning to compute arctan of 1/16. Now, I have no idea what arctan of 1/16 is. I know what arctan of 1 is. I know what arctan of √3 is, or 1/√3, because those are common values for arctangent, but I have no idea what arctan of 1/16 is. So how would we figure this out if we needed to know it? So I'm going to compute this using the series from the first problem. Okay, so the series from the first problem was where we figured out arctan of x squared is the sum from n equals 0 to infinity of -1 to the n, x to the 4n plus 2 over 2n plus 1. So that's the series that we got before here. Okay, now you might ask, okay, well, could we have just done this with, like, the vanilla arctan series and then just used 1/16 instead of plugging in x equals 1/4? And the answer is yeah, you could have done it this way. I just wanted it that way. I just wanted to get more usage out of the series we already found. So if I want to know what arctan of 1/16 is, well, that's the same as knowing what arctan of 1/4 squared is. So it seems like I'm going to plug in x equals 1/4 in order to figure out what this is going to be. All right. Is this example 2? Oh, no, sorry. Yeah, it was example 2. My mistake. We'll have problem 2 in a little bit. So if I plug 1/4 in here, which is within the radius of convergence, as it goes all the way out to 1, we have 1/4 to the 4n plus 2. Now in this one, rather than having a particular error for this, I want to compute this using the first 3 terms of the series. So that's kind of the 2 ways people can ask you to do approximation. The first way is they can ask you to get within a certain error tolerance. And then the other way is use a certain number of terms from your series. So we're going to do it that second way this time. All right, so arctan of 1/16, which is arctan of 1/4 squared, is exactly equal to this series. So this is a regular equal sign because we go all the way to infinity. But while we can't realistically add infinitely many numbers together, even on a computer, we could probably add 3 numbers together without too much difficulty. So let's do that. So I'm going to add in n equals 0. I'm going to plug that into here. -1 to the 0 is 1. 1/4 to the 0 plus 2 is 1/4 squared. And then I plug 0 into here and I get 1. So that was the n equals 0 term. Next, I have n equals 1. So I have a -1 here. So that's a minus. I plug 1 into here. Now I have 1/4 to the 6th. And then I divide by 1 times 2 plus 1 is 3. And then my last term, so I wanted to add the first 3 terms. So I have 0, 1, and then 2 right here. So I plug in n equals 2 into here. -1 squared is 1, positive. I have 1/4 to the 4 times 2 plus 2. So that's 1/4 to the 10th. And then I divide, I plug 2 into here, and I get 5. So while, of course, this isn't exactly equal to this because we're missing infinitely many terms, we hope that maybe adding the first 3 together will give us something pretty reasonable here. So what is arctan of 1/16? It's what you get when you combine all of these fractions together. And I don't want to do 4 to the 10th power. That's starting to get kind of big. So I'm just going to leave it like this. So arctan of 1/16 is approximately equal to whatever this is right here. Okay, now I also want to know the error. And I could probably speak for any field that you guys ever enter in, whether it be engineering or science or any kind of quantitative field. If you ever make an approximation, you need to know, have an upper bound on the error. Because, for example, you could say, oh, Gainesville is approximately 3,000 miles from Miami. And while that's technically true, the error bound on that would be very large. So that wouldn't necessarily be a very good approximation. So we always want to have an upper bound on our error here to let us know how good our approximation is going to be. All right. So let's see here. Now, this is, again, an alternating series, right? And I used S2 to approximate this. Now, remember, this is S2. It goes up to n equals 2. It doesn't mean it has 2 terms. So we go up to 2, but there are 3 terms total. All right. So remember, the error between S2 and the true sum of our series, which is this, 4n plus 2, 2n plus 1, that's got to be less than A3, right? According to the alternating series remainder estimate here. All right, so what's A3 here? Well, we got A2. A3 would be if we plug 3 into this. We ignore the negative here. The A3 here only counts this stuff. We have 1/4 to the 3 times 4 plus 2. So that's 1/4 to the 14th. over 7. This is 1 over 4 to the 14th times 7. And I actually went on a calculator and did this earlier, just to give you a sense of scale. This is 1 over 1,879,048,192. So what this means is that only adding up 3 terms of our series got us to within 10 decimal places of the true answer for arctan of 1/16. So, 3 doesn't seem like a lot compared to infinity. It's literally nothing compared to infinity. But only adding up a few terms can get you an incredible amount of accuracy. So this is greater than the error. So our answer is no more far off than this is right here. So this kind of demonstrates the power of power series. You don't need to add up too many terms to get an accurate approximation. And by the way, 10 decimal places for a scientific calculator, that's all the way across the screen. So all your scientific calculator needs to do to get things like this is add up about 3 terms. So it doesn't need an excessive amount of computing power. All right, so why don't you guys try this? Here's practice 2. So kind of in the same way, I want you guys to approximate ln of 9/8 using the first 3 terms of the series from practice. And how far off is this? At most. So just a reminder, let me write down the series we found earlier. Ln of 1 plus x cubed is the sum from n equals 0 to infinity of -1 to the n, x to the 3n plus 3 over n plus 1. Oh, GeoGuessr. I'm so bad at that. Yeah, so be careful about what x value you try to plug in. Remember that there's a 1 included in the natural log as part of the series. I'll give you guys another minute or so. Oh, wow, I actually finished early today. Nice Friday treat. Upper value of x is still 1/2. Yeah, 1/2 would be a good x value to plug in, because if you cube 1/2, you get an 1/8, and then you add that to 1 and you get 9/8. So x equals 1/2 is the way to go. All right, let's take a look at this. So yeah, based on what I just said, x is going to equal 1/2, because we have ln of 1 plus 1/2 cubed, which is ln of 1 plus an 8, which is ln of 9/8. All right. So that means if I plug 1/2 into my x here, I can also plug 1/2 into my x here. So I have n equals 0 to infinity, -1 to the n, 1/2 to the 3n plus 3 over n plus 1. But remember, 1/2 to the 3n plus 3 is the same thing as -1 to the n, 2 to the 3n plus 3 times n plus 1. Okay, now we want to use the first 3 terms of this series. So let's write this again and then do an approximation. -1 to the n, 2 to this power, n plus 1. That's approximately equal to, all right, our series starts at 0, so let's do that. So we put 0 in here. We have 1 over 2 cubed times 1. So that's going to end up being 1/8. All right, next, we plug 1 in here. So we have a minus. I'm going to get 2 to the 6th, which is 64. And then I multiply that by 2, gives me 1/28. Okay, and then for my final term here, n equals 2, I plug 2 into here and I get a positive. I have 2 to the 8th power. Wait, no, wait. Oh, no, I'm sorry. 2 to the 9th power, which is 512, times 3 is 1536. But I think in the Chronos, it may, or in the Canvas, it may be 2 to the 9th times 3. But that's what we get here. So if we combine all these fractions together, that's going to be our approximation for ln of 9/8. Okay, now how far off can this approximation be at most? Well, remember, the way to detect that for an alternating series is to simply look at the next term that we would have added. So our error is less than A3, the next term we would have added to this. And what's A3? Well, we plug 3 into here, and we have 2 to the 12th power times 4. All right, let's see if I know my powers of 2. 1024, 2048, 4096, 16,384. So our answer is no further off than that right here. So about the 4 or 5 decimal places with only adding up 3 terms right here. What do I mean by the first 3 non-zero terms? Well, if you ever happen to plug in an n into your formula and somehow it ends up being 0, you don't count that as a term. So let's say maybe n equals 1 ended up giving us a 0, for instance. Then we would do n equals 2, but then we would also go on to n equals 3. We want to make sure we get 3 non-zero terms here. By the way, one point of confusion, non-zero does not refer to this. It refers to what the value of this is. So non-zero doesn't mean we exclude the 1/8 right here. Non-zero just means if one of these end up being 0, then we would skip it and move on to the next one. All right. Well, there we go. We got done 5 minutes early. So what we're going to do next week is we're going to learn how to find series for other types of functions. Like I foreshadowed this with saying we have sines and cosines and e to the x. We can find series for those. We're going to find series for those and many different functions in general. And then we're going to see more applications we can do. So we're going to do more stuff like this, but then we're also going to do some additional applications even beyond this stuff. And then we'll finally get to the question some of you guys want to know. Where is this sum of all the positive numbers being negative 1/12 come from? We're going to talk about that next week as well. But anyways, yeah, that's it for today. So I will see you guys on Monday.